So what I wanted to get out of the meeting today is I wanted to better understand how to help the Recon folks use the SZ3 module library to extend it to incorporate
Yes.
code from TEZip.
Hmm.
And I wanted to understand some of the trade-offs and better how to use the difference between the predictor interface versus the decomposition interface. So at a high level, that's kind of what I'm looking to do. And then I wanted to talk a little bit about passing additional configuration parameters down into both either predictors or decomposition. Um, so at a high level, that's what I'm hoping to cover in this meeting, and then we can kind of go from there.
Okay. First about predictor and decomposition, I think now most of the code using decomposition instead of predictor. Let me
Okay.
double check. This is a 3.3 branch.
Yep.
Um, I think predictor, like the only left predictors are Lorenzo and regression. Those are kind of block-wise
Yep.
predictor. And for other like interpolation, those like non-blockwise design, I all put them into decomposition.
Okay.
It's
That's kind of what I was wondering because I noted in the old design, I think interpolation was a predictor, but now it's been moved over to decomposition, which probably makes more sense.
in the old design interpolation is still like a decomposition because it use prediction and quantization alternatively on each data point. So we cannot separate those two modules. So if
Hmm.
we separate, then we need to like collect all the prediction data and do the quantization, and that will slow down the interpolation. So when writing the code, I like mix them for each data point, prediction and quantization. And due to that reason, I put the like decomposition interface.
Hmm.
So that's one thing. Another thing, for the for the Rican people, so they just want so what their code do is just a prediction, nothing
Yeah.
else.
So essentially what it does is it decomposes the data set into a series of tiles, and then
Mm-hmm.
each tile is fed asynchronously to the GPU,
Mm-hmm.
where they use libtorch to perform a prediction of basically given a subset of the tile, it tries to complete the tile. And if that prediction is successful within a certain error bound, they just store a couple of anchor points essentially that describe the tile as a whole. And then they kind of repeat this process iteratively over the z direction or the z dimension. So the 2D case is exactly what I told you. In the 3D case, what they do is the first image is treated as what's called a keyframe. So it's compressed losslessly
Mm-hmm.
in its entirety. And then the next K frames will be stored as a difference relative to the keyframe. And they kind of repeat that until the predictions from the keyframe to the ith frame are no longer reliable.
So
Um,
you okay now so if it's reliable means within the error bound or within 10 times error bound.
they still do error bounded lossy or they still do an error bounded prediction correction scheme even on the keyframes. What unreliable means is that the um, average error in the prediction exceeds some threshold.
Okay.
So if they take the total error, or excuse me, the total error exceeds some threshold. So if the total error in the prediction starts to get too high, then they create a new keyframe and then they keep going.
Okay. Okay. I see. So if the like if a tile is with all the dead points inside the tile, um, where the prediction is within the error bound, then they will not store. the quantization data, right?
Yeah. So as I said again, it's not so much the error, right? Because you're still going to keep the error underneath the error bound, right? Because you're still doing a correction scheme within each frame. But if you look at the prediction error before decompression and just the prediction error before you perform any correction with lossless values, like you do in a Z, what they say is if that total error exceeds some threshold, then they treat it as something that they're going to trigger a new keyframe on. So
Okay.
it's so
Yeah.
yeah, so like while the individual, like if you decompressed it and looked at the error, the decompressed error would be below some threshold because for all of the frames, even the ones that would trigger the creation of a new keyframe. It's only when the prediction error, but not the decompression error, exceeds a certain threshold do they create a new keyframe.
Okay. Okay, I got it. So yeah, besides the keyframe, I just want to double check like for each tile, like for every data point, like if the estimation is prediction is pretty accurate and the difference prediction error is less than the error bound, do they still like if we treat their function as a black box?
Yeah.
Is
So if ignoring keyframes,
mm-hmm.
so if the prediction error on an individual point exceeds the error bound, then they use the lossless encoded value, just like you do in a Z.
uh if the prediction error exceeds the error bound, then they use uh
The lossless value. So they
lossless value. So they do not do quantization.
so they may still do quantization, but my point is it's just like a Z. So they have an unpredictables array that they accumulate values into.
I see. Okay. So that's so, so that they have that internally, right?
Um,
So do we want to
so
treat it as an
yeah,
internal thing?
so the discussion was around like um what is the best way to kind of expose their technique, their prediction scheme to the EVZ framework so that it can be used as a module as part of some larger or composite prediction scheme. So the idea you might imagine would be, let's say you have certain regions of the data that are much more chaotic, that maybe going all the way to an AI model would improve the prediction accuracy for some small region. So in those regions, they want to leverage the AI model, but in the rest of the image, maybe you want to use traditional Lorenzo or traditional interpolation for other regions of the image. So you might imagine like a composite prediction scheme that maybe takes some coordinates that tell you where you should do this AI thing, and then other coordinates where you're going to do the
Okay.
fallback method. So if you wanted to facilitate the creation of techniques like that, the first step to me seems like you need to have some way of telling SZ about this new prediction scheme.
hmm Okay, I
Um,
got I got
and
it.
yeah,
hmm
and my first impression, just from my memory of SZ3, and admittedly, my memory of the fine-grained day-to-day details of SZ3 is a little dated at this point. But my understanding was that the prediction mechanism was the most closest analog for performing that behavior. Because we
mm
want to do almost exactly what you do in the Lorenzo case, except for we're doing predictions for an entire block at a time, and then we're kind of sorting out what we want to do after the fact with those predictions.
Okay. let me see. So, if we do that, then for the prediction interface, currently it's only like
Yeah, so currently it's an element-wise prediction. So if you wanted to do block-wise prediction, you'd have to like know the fact that it's going to iterate through it in block order, and then you'd have to kind of cache um, the predicted block in order to get the performance remotely close to what you're hoping for. At least
mm,
that's my understanding, which is fine. Like I was planning on doing that piece.
let me see. This is point-wise, but we can also let me where is code block-wise decomposition? That's because I put the block-wise code to decomposition interface.
Hmm.
So those are the code that goes through each block to call the prediction interface.
Hmm.
Like there is a iterator called for each function to go through every data point. And if we want to like use Lorenzo and the AI method together,
Hmm.
mm, what's the best way? This is one block. Then in this block, let me see, we need to test. We need to use a mechanism to test which method has a better result. Maybe use some estimation. Then
Well,
we call.
yeah, so either it could be like the scenario that I proposed, it doesn't even necessarily use an estimation. I just said suppose you give it coordinates, in which case you look at, I guess it's this index value,
Yes.
and you use that to decide inside of that predictor which one you delegate to.
Oh, just use index. Okay.
So I think that still works.
Okay.
Um, So the index that's here, this is the block index. So like the index of the first
So
block would be 000, and then the next blocks would be with like 001, or would it be 00K, where K is the stride?
this is the index within a block.
Oh, so this is the index within a block.
Yeah, but I think we have another function to tell you the index, global index.
Okay.
That's a small thing to like just update. Um, Let me think. But for the AI master, if we yeah predictor, we put it the predictor. Mhm. Yeah, I think the easier way is still to use put it in a decomposition.
Hmm.
Basically, we copy this block-wise composition to something like, I don't know, AI composition.
Yep.
and and add some logic like if where is this block get data range. There should be something like block index, something like that. Then equals something. Then we call the AI method.
Yep.
Yeah, I
Yeah. So
also
that
would
that
do.
would be how we would do what that's how this is how we would do um but hold on, where is block defined here?
Block is
The
defined
block is
here.
just an iterator, and you're iterating it over with the do while loop.
Yes,
Got it. So block.next advances the iterator. Got it.
yes.
Okay. Um, yeah,
Yeah,
so the get block index currently doesn't exist. But supposing that it did,
Yeah, I can add it. It's no big deal. I think it exists, but not the same name. I need to double check.
yeah. Okay, that's fine. Um, okay. So the AI, so that kind of talks about implementing that higher level strategy that I talked about, where like you're gonna check the block indexes or whatever for handling the that handles the case where we want to do this hybrid thing. But if what's the most appropriate interface for the code, the pseudocode here that says call the AI method? Do we just implement a case of predictor or
Yeah, let me ask a question. So for their method, so they return the prediction results, or they return some prediction error that has already been quantized.
so ultimately they retain some prediction error that's quantized. So they operate on an entire block at once. They send it all off to the GPU asynchronously, and then they process it on the GPU because each block that they're processing, it's bigger than an SZ block, because that's what they need in order for the GPU performance to be what they need. Um, but they're sending concurrently many of these blocks to the GPU simultaneously because while they're larger than an SZ block, they are not sufficiently large that it's not like the whole data set at once. So I think their block size is like 100 by 100 by 100 or something like that.
Yeah, that makes
Um,
sense.
and they might be running, say, four of them concurrently on the GPU.
Okay. Yeah, that block size makes sense for AI. So they write on GPU and they return some quantized integer. Then
Yeah,
it's
so
a
they get back like a uint8 array,
okay.
a uint8 block, which contains the quantized values.
Okay. So that's a let's follow the decomposition design. So decomposition is convert those floating point data to integer to some
Okay, and it
quanti.
just returns a stood vector.
Yes,
Okay,
it's a vector with you define the type. You're like defined as int. Int 8 should be fine.
okay,
So basically, this is original floating point.
okay,
Yeah, I think decomposition is in this case is better than prediction because they handle some quantization themselves.
okay. What if they didn't handle the quantization? Would it still be decomposition interface?
In that case, I think yeah, I think it's still a decomposition interface, but we need to just add the code like what we demonstrate. This is a decomposition.
Yep.
Basically, you take the data as original and you call the, let's say the method is AI, and you call the data and you get, oh, data block. Let's say you have a loop, go through each.
Yeah, so my impression here is you would call some constructor to create the multi-dimensional iterator that iterates by
Yeah,
block,
yeah,
and
and
then you loop over that with the do while loop.
yeah, and essentially inside loop you have the prediction
Yep.
data, and and then we do the quantization. This is not number, this is block, number per block. Then we
Yeah.
call quantize.
Yeah, and the quantizer here is just an implementation of the quantizer interface, I think.
Yes,
Okay.
something
Um,
like
so
this.
another thing that's probably important for performance for them. So I don't know if you knew this or not, but you know that there are multiple template parameters to stood vector.
Uh, to what vector?
To stood vector, it has more. So if you look at the definition on CPP reference for stood vector,
Vector?
yes. So
Okay.
stood vector has two template arguments.
Two? Oh, you mean the number and the value, something like that?
No, so stood vector of int that can
Yeah.
have a second argument.
Okay.
Um,
Right.
so, so the second argument is an allocator.
Oh, okay.
And the reason why I mention this is that's how CUDA with thrust implements thrust device vector. So thrust device vector is just an alias for std vector, or at least at one point it was just an alias for std vector with an allocator that calls CUDA malloc
Mm,
um, as the second template argument.
okay.
And so the reason why I'm mentioning this is if you're returning data that's on the GPU, right, you don't want to necessarily copy it back to the host if you don't have to.
Oh, okay. So what's like, does it, let me see.
Because std vector with the standard allocator was std allocator. So the second argument by default is something called std : allocator of int.
Uh-huh.
So that's the default argument that is assumed if you write just std vector of int.
Yeah, yeah, I think I understand this part. What I don't understand is about CUDA. In my understanding, for the device to host and host to device copy, the programmer need to do it themselves, right?
Not necessarily. So there's something called thrust. Are you
Oh, so I
familiar
can
with
control it
thrust?
automatically? Okay.
So in thrust, there is something called thrust device vector.
Okay.
And thrust device vector is a variant of vector where the memory is backed by CUDA, not by the host. Um, so it's
Okay.
GPU memory, not host memory. So you can't on device code, or excuse me, on host code, you can't do like square bracket of 0 on a device vector. And you can't dereference a iterator on host code of a device vector. Does that make sense?
So so the code initially like the data, this data initially is in CPU, right? So like the thrust vector can pass this to thrust vector, then vector can automatically copy this to device.
Yes.
Okay. So
Um,
once it copied to device, then there is some limitation. That's what you mean?
yeah. And
Okay.
but so then you would call your AI processing methods, right? But because everything's already on the GPU
Mm-hmm.
or has been copied by block to the GPU,
Mm-hmm.
um, you don't necessarily want to copy it back to the host if you don't have to.
Yeah.
So this kind of goes to what we were talking about a couple of months ago with the QSZ discussion of there are certain things that GPU enabled compression needs out of the interface in the module library to facilitate good performance on GPU. So, for example, if the user provides you a data that is resident on the GPU, you'd like to not copy it. And there's a CUDA API that lets you know if a particular pointer is a device pointer. So you can check this API, know that it's a device pointer, but then you don't want to return then a std vector of int. You want to return a std vector of int of CUDA allocator.
I see.
Instead, now do you kind of get what I'm talking about?
Okay. So let me see.
So
Essentially, we need to change this, right?
yeah, so specifically what I think we want to do is I think we want to add a fourth template argument to decomposition interface and potentially some other places as well. That is a std allocator. And by default, it's just std allocator, which calls malloc and free. So we do exactly what the C++ standard library does with std vector, but instead the user can choose to provide a vector of CUDA
Mhm.
to support that. You get what I'm saying?
Yeah. How
Um,
about we chat to do this?
so the challenge with doing that is then you don't know at all what could possibly be returned from compress. I think that would make it very hard to work with.
But it gives more flexibility if user want to use like their own structure instead of the like.
Yeah, it's a fair question. I don't necessarily know the right answer, but I think so. Yeah, and then the other thing here is what if the user wants to provide the memory that should be used for decompression or used for compression? So you want to pre-allocate. So ZFP has this function. I don't know if you're aware of this or not. Um, I'll share my screen in just a second.
Okay.
Um,
We have a higher level API to like take the pre-allocated memory.
oh, you have a higher level API for pre-allocated memory?
Yes.
Okay, so we'll look at that in just a second.
Okay.
Okay. So there's two things. So one, ZFP as well as a bunch of like CUDA optimized libraries provide routines like this. So if you look at like, for example, the CUDA BLAS implementation of gem, if you pass a null pointer to the gem routine in CUDA BLAS, it just tells you how much space you need in order to perform this calculation, both in terms of the output space and potentially any auxiliary memory that needs to be allocated. So that's exactly what this does. So
I don't understand if the data is null, then how it estimate? It's just a
it's a worst case estimate.
okay,
So it says even if everything possible went wrong,
okay,
which is what this ZFP stream max size returns,
okay,
that's how much space it allocates.
okay,
And in the case of LibPressio, the way that it communicates that is it says it's going to need this many bytes. And because it's returning an empty buffer, there's no allocation associated with this. It's just kind of some metadata. It's just returning some metadata saying how large this thing can potentially be.
okay.
So that's kind of the first thing that you potentially need for GPUs. The other thing that you potentially need is if
I have
you,
a similar function.
okay. Uh,
I say compress bound to tell you what's the like maximum size for the buffer.
okay. Um, so the second thing here is when you see outsize. So outsize here, that's if you handle an error. So there's this if reuse buffer. So if the output buffer has space, reuse buffer is set to true, and it just uses the memory directly from this. Otherwise, it allocates some memory, and then it does this operation to tell LibPressio to take ownership of the data that it's working with.
Okay.
Um, so in this way, you can kind of pass some memory into LibPressio,
Hmm.
and it can use the memory that you provided it. So is there an
Yeah.
equivalent set of APIs in SZ3?
Yes, let me show you. But it's a high level, it's compressed, no decomposition. This is the SZ.hpp. This is the high
Yep.
level API. But essentially, we have two compression methods. Uh, they take the, like we say, I say compress. They take similar parameters. Just this one takes compressed data, which is already a buffer,
Yep.
and this is a buffer
The
cap.
capacity. Yep.
Yeah. And if you do not have that, then you can call this. And inside this, I create a buffer for you with the buffer length as a
And
bound.
got it. And it uses this compressed size bound.
Yes.
Okay.
Yeah, I think it's similar with the FP now. And
Yeah,
for
that's pretty similar.
yeah, for decompress it's the same. We have two functions. It's just
Yep.
the last parameter. If it's the pointer is null, then what?
Yep.
Create a new, I think here, yeah, create a new memory space to store. If it's not null, then no need to create, just use whatever the user passed.
Got it. So when SZ returns something, the capacity is potentially the capacity of the memory returned by SZ is potentially bigger than its size. So it may return a 2 gig allocation to hold 100 megs of data.
Uh, Let me think. For return, this is just an input parameter.
Yeah. So in this case, you can exactly right size the allocation, but in the other case where you don't provide memory,
then I will create an upper bound, and this will take
yeah,
yeah,
yes.
yeah,
So
take a
you
lot
could
of
pretend,
space.
yeah,
But I actually here I still check the bound. So if like if your input data is 1G, then if the cap is only 500 MB, then it's still throw error. Even if
I
you
see.
are, yeah, even if you think it should be fine, but we don't know before we compress it. So
Yeah, fair enough. Yeah, and I understand handling it there from an implementation perspective. Okay. Um, but if we go back to so if we go inside of the call to actual compress, right? So back in the z.hpp,
oh, okay,
so ultimately it calls z compress simple,
yeah, this is
and then
just a
that calls either the OpenMP or the dispatch, and then it calls z, I guess,
yeah,
compress Lorenzo just to pick one,
yeah,
or interp is fine too. Okay, and then ultimately it makes a generic SZ with a
decomposition,
decomposition and then
encoder,
an
lossless.
encoder and a lossless stage.
Mhm.
Um, so what's the return type of arrow compress? Oh, actually, arrow compress. So can you go to the definition of arrow compress?
Oh, this one, the
Yeah.
size.
Can you go to
The,
the definition of that?
yeah, it returns the size here,
Yeah. Okay, so
the compressed size.
it just treats the quantization IDs as a vector at the end. So it's just using it as temporary storage. So whenever it writes the ultimate thing, it's
You
gonna
mean
write it.
this? Uh-huh.
Yep.
Yes.
Okay. Okay. Um, this was helpful. I think I have a better understanding of how things fit together.
Okay, to support GPU, maybe I need to uh yeah. So here we need to change it. Mm.
Well, so that one can still potentially be stood vector, right? Um,
But what if this is a GPU decomposition?
So if you can, so you know that this is copy assignment.
Hmm.
is that what that form looks like. Actually, I guess it's move copy assignment. So this is going to move assign. So if you move assign a device vector to a host vector, the move assignment from a device vector to a host vector copies to the host.
I see. Yeah.
Or,
Mm. Yeah, and
so,
we needed to copy to the host because we need to do following Huffman coding.
yep, exactly. And the Huffman encoding is implemented on the CPU. So if you had a encoder that was GPU aware, then
Then we need to change it.
yeah, then you would need to change that. So what you might consider doing is make the have you heard of the traits pattern or the type traits pattern?
Mm, not particularly.
Okay, so basically you can put a type definition. So if you look at the CPP reference for std vector and just the overall documentation for std vector.
Okay, I'm on that page.
Okay, so you see where there's a section that says member types.
Uh, what types?
In the CPP reference documentation, there's a member types section, and you'll see
Yeah,
like
yeah,
value type,
yeah, yeah,
allocator
yeah.
type, size
Yeah.
type, difference type, so on and so
Yes.
forth.
Yes.
So encoder could have a quantization type or a decomposition type or an input type. So then this first line on 39 would be encoder colon colon input type, which in this case is a std vector event. You understand what I'm saying?
Uh, no.
Maybe I can write some sample code.
Okay, stop sharing.
There we go.
Okay,
You could
I
also,
think, yeah, I think I got the idea.
yeah.
So you want to link those tabs from the like begin from the
I mean,
previous module to the following module.
yeah. So this is just kind of the rough idea, but
Okay, I got it.
yeah.
Let me take a screen. Could you could you share the code or the
Yeah, I'll
screenshot?
share this code, but I will also send the recording to you
Okay.
after this meeting. Um,
Okay.
but I think that's all that I wanted to touch base on this morning. Did you have anything else that you wanted to talk about?
I think you also asked a question about configuration, right?
Oh, yes, the configuration. I forgot about that. Yes.
So I also updated the configuration. Now it has basically two set of functions. Where is whatever. So let's use this. So for config, it has basically one set of function is serialization and deserialization. We
Yeah.
we put it in binary, and another set
Yeah.
of functions are uh kind of
Yeah.
save to text and load from text.
Yeah. I guess my question is
So
if
yeah,
someone wants to produce a third-party module,
yeah, they just add the
yeah, But like, let's suppose we have 100 third-party modules.
Hmm.
Does that, and each one has 1 to 5 parameters that they want to expose.
Hmm.
It seems like this struct would become unwieldy somewhat
Yeah.
quickly.
Yes, maybe we need to change to level. Um,
Yeah.
yeah,
So
but
so
if we
maybe
yeah, go
yeah, so
ahead.
so maybe config needs to be a template class.
Template class.
So in this case, it's just a plain old struct with these parameters in it, right? But
Hmm.
if it's a template, then the user can provide any struct as long as it has the set of names that correspond to their specific. Because if you look at the code, config is passed as a concrete type a lot of different places in the code.
Yes.
But
Currently
if you
the
want people to be able to expand config, do you understand what I'm saying now?
so we want to allow them to define their own config, right?
Yeah,
And they can pass their own config. And
yeah. Because it, like, for example, if you have a config that takes like 2 MB of space to store, it doesn't make sense for every user of SZ3 to be penalized by the fact that somebody created a module with 2 MB worth of config.
yeah, that's what I want to say. So for the save and load, we just save and load the shared variables. For the module specific variables, they do save and load themselves.
Yeah. And I think that's the right thing, right? That the configuration should save and load the variables that it cares about. But I think,
And for a specific module, it has multiple like uh like those are module specific parameters, and inside this config, it does not save or load those variables. So it saves
mm,
only those like arrow bound, which is used for not only prediction but also quantization.
yeah. So what I'm saying is if the compress functions that take a config instead take a template config, if the user wants to declare a new class that has its own config, they don't need to modify this one or to force other users to use this config. I understand there's reasons not to do that. So if there's a better answer, I'm open to other answers. I think it's going because at this point, like you can't extend the library without changing this file. You have to replace config.hpp if you want to provide a third-party module. There's no way to leave the base code of SZ3 immutable and provide configuration to a new module.
Let me see. If we make this like a template, they still need to So there are multiple modules. Each module has their own config. Then for a compressor, they still need to take all those files from different config. Then
Yeah. So the other possibility is you have like a map like structure, and you the other possibility is you have a map structure, and but that's going to suffer access. It's not going to be as easy for template code to the compiler to unwind, if that makes any sense.
Mhm.